All right, so this is our second set of slides. This is Circulation of the Ocean Part 2. And we're going to talk about deep ocean currents. And we're going to start again with the forces that drive these currents. So we have temperature, salinity, density, and gravity. We're going to spend quite a bit of time talking about those, and then we'll see what effect the wind has on the deep ocean currents. As you might imagine, because the wind does not blow over the deep ocean, it's going to primarily affect the surface currents, but it turns out that its effect on surface water is going to have an impact on the deep water and what the deep water does. So the general circulation of deep currents is shown in this figure from your book on the right. We're going to look at places where the water sinks. This primarily occurs when the water gets cool and more dense, and it tends to rise when it gets mixed and the surface water, which is heated, moves off to the side. This is kind of a classic style of convection, which we learned back in Chapter 8. So if you want to review a little bit about convection, you can go back to Chapter 8. But we'll talk about it more specifically, exactly what's going on here in the next few slides. So first of all, let's talk about downwelling. Most of the deep water forms in polar regions, and so we want to focus on this first bullet and the parts that are underneath it. In polar regions, it is cold, and the water tends to freeze. If you remember back to our chapter on ocean physics, the physical ocean, I believe that was chapter 6, one of the things that we said was that when the seawater freezes, it extrudes the salt. So the water freezes, the salt does not. What that means is that the water directly underneath that sea ice is both cold and extra salty. And because it is cold and salty, it is more dense than the surrounding water. And because it is more dense, gravity is able to pull it down to the deeper part of the ocean. So we actually have kind of the primary thing that's going on here, which is the formation of cold, salty water under the ice, results in the second item here, which is the greater density, which allows the third item, gravity, to act on this more dense water and pull it down into the deep part. And this is really our primary type of downwelling in the ocean. And it happens in the North Atlantic when sea ice forms. It happens to some extent underneath the sea ice that forms in the Arctic Ocean. And it also happens around the edge of Antarctica, so in the southern continent or in the southern hemisphere as well. So we see this happen in both the north and south polar regions. This cold, salty water forms and sinks. There is another kind of a smaller place where downwelling happens that's mentioned in the book, and that is the Mediterranean Sea. Now, in the Mediterranean Sea itself, we have a closed basin near the equator. There is a lot of evaporation that occurs. And so the water is not only warm, but it's also salty because water is evaporating. That makes it slightly more dense than other seawater. And so as water leaves the Mediterranean Sea through the Straits of Gibraltar, it sinks a little bit. It doesn't go all the way to the bottom. It simply goes part way down, and we'll see on a side view of the ocean in a little bit exactly where it ends up. But it is also pulled down by gravity. So the third thing that's listed on this slide is the wind. And the wind can basically push water down when there is no other option. And what they're showing here, it's kind of complicated, but to keep it simple, the best way to think of this is that the wind is pushing the water toward the shore. So it's a little more complicated because of the direction of the wind and Ekman transport, which is described in your book. You don't need to worry about that. What I want you to remember is that when wind pushes water toward the shore, some of that water sinks down to make way for more water. And so that can be a cause of downwelling. But you'll notice in this instance, it's not density driven. And so that water is going to be a little bit easier to bring back to the surface when the conditions are right. Now, how does the water get back to the surface? Well, wind becomes a really important factor here because wind can pull it back up to the surface. And so if wind moves water away from a coast, so just the opposite of what we were just talking about, or if the wind patterns move the water away from an area like we sometimes see along the equator, that can result in water being pulled up from the bottom to replace the water that was removed. And so this is really the primary cause of focused upwelling. If we go back to this slide, you'll notice that some upwelling is just basically spread out throughout the ocean, that deep water spreads and mixes and finds its way back to the surface. The upwelling that we're talking about here is more focused. And this upwelling tends to be very important because when this water comes back to the surface, it brings a large quantity of nutrients with it. So it's cold water, but it's very rich in nutrients. That rich in nutrients part means that when we talk about life in the ocean, these areas of focused upwelling will be places where we see a lot of photosynthetic life, because the photosynthetic organisms need those nutrients. And then because they're very abundant, things that feed on them are very abundant as well. But the thing to remember right now is that this upwelling is basically water pulled up to the surface to replace water that has been moved away by the wind. And when we put this all together, we get what we call a thermohaline circulation. Now, if you break apart that first word, thermo refers to temperature, haline refers to the salinity of the water, and so thermohaline circulation, if we go back here, we see cold, salty water is more dense and it sinks. That's really where that name comes from. It's this cold, salty water, more dense, sinking down into the ocean. And there are a number of different water masses that they are going to show you in a diagram coming up. But basically, what you want to think about is water is going to find a level where the more dense water is below it, the less dense water is above it, and its density is controlled by its temperature and its salinity. So if we go to the next slide, we can see this graph, which looks very busy, and it is. The main thing I want you to take away from this is that the factors affecting density are salinity and temperature, and the density that we get is a combination of those two. So warm, salty water is going to be more dense than warm, not salty water. And cold, salty water is going to be the densest of all, but we can have some water in between that, because of its temperature and salinity, has some density differences as well. And you'll notice that those densities are not really large numbers. 1.023, 1.024, a small difference in density is enough to allow a water mass to find a different level. So, very complicated drawing. Don't worry too much about it, except for the fact that salinity and temperature are going to determine the density. The better diagram to look at is the one here in the lower right-hand corner, where you can see how all this plays out. We have the surface water, which is very warm and therefore less dense. That's red on top. And then we have the deep water, shown in blue and dark blue. The lighter blue color forms near the North Pole. The darker blue color forms near the South Pole. And those waters are of different densities, so they end up at different levels in the ocean. That Mediterranean water is going to end up somewhere in that kind of between the light blue and the pink. And these water masses move very slowly across the bottom of the ocean, and as they do, they mix with other water. The density kind of evens out, and it can slowly rise to the surface. But as we mentioned, there are places where the wind can pull some of that water up to the surface, and those are the upwelling zones. When we put this all together in a giant map of the planet, we can add the gyres in with the upwelling and the downwelling, and you get this map that they have in your book. It takes 2 pages when you open up your book. You'll notice there are U's, places where there is significant upwelling, and there are some indicators, some S's for the downwelling or the sinking water. And so you can see the connections between these surface gyres and the deep water flow as well. The book then also discusses something called, that you probably have heard of, which is El Niño or El Niño Southern Oscillation. And this is just one particular ocean circulation pattern that occurs that we have come to notice. It happens in the South Pacific. On the right-hand side of each of these diagrams is the coast of South America. And on the left-hand side is the coast of Australia or Indonesia. And you'll notice that in normal conditions, there is upwelling along the west coast of South America, so the east side of the Pacific Basin. The wind is moving water away from the coast and giving us some focused upwelling. That feeds a very important fish hatchery. It keeps the climate a little bit cooler and a little bit a little bit drier. In an El Nino year, the air currents change and the ocean currents change. Places where you would have upwelling, you have downwelling. Places where you would have downwelling, you might have some upwelling. Places where you would have rain, you get a dry year. Places where it's normally dry, you might get a wet year. It just kind of shifts many of the normal patterns around. And you can see in El Nino Southern Oscillation that very, very close relationship between ocean circulation and air circulation and weather and climate. And so that's the last slide that I'm going to discuss. If you look through the slides that are posted online, you'll see there are some summary slides to end up this particular slide package that puts the chapter in perspective and goes over some of the key concepts. And with that, I will end this recording.